Assalamualaikum YouTube viewers. The topic of today's video is the conclusions from the study of particle in one-dimensional box. So in this video we are going to describe the conclusions that have been taken from the particle in one-dimensional box. Okay. So first of all, what was the first conclusion? The first conclusion was the quantization of energy. Okay. So from the solution of Schrodinger wave equation of a particle in a space, we can explain the quantization of energy. Do you know what is meant by the quantization of energy? The quantization of energy means that the energy is quantized, means it is in the form of packets. It means that the energy is absorbed or released in the form of packets called quanta. Okay, it means that our particle does not emit energy continuously, but it emits energy discontinuously in the form of packets. The quantization of energy means that our particle does not emit energy continuously, but our particle emits energy in the form of packets called quanta. This is known as the quantization of energy. Okay, so first of all is the that from the solution of Schrodinger wave equation of a particle in a space, we can explain the quantization of energy. By using the Schrodinger wave equation, we can explain the quantization of energy. The next thing is the expression of energy from Schrodinger wave equation in one-dimensional box has come out to be equal to E is equal to n square h square over 8m square. This is the expression that is obtained from the particle in a box in one dimensional box. Okay, so first of all what we are gonna do is to derive this expression. Okay, as you can see here, n is an integral having value 1 2 3 and so on. So the energy associated with each value of n, okay, if I take n to be equal to 1, I get an answer equal to, if I take n equal to 1, okay, if I take n equal to 1, then I get the value of energy to be equal to E is equal to h square divided by 8ma square. Okay, so if I take value of n to be equal to 2, then I get an energy equal to 4h square divided by 8ma square. Since I have taken n is equal to 2, 2 square becomes 4, that 4 will that 4 has come here, so 4h square over 8ma square. Okay, so as you can see that our energy h square over 8ma square, it is an integral multiple of n square. Okay, only the value of n are changing, and we can say that h square over 8ma square is the multiple of n square. Okay, it occurs in the multiple of n square, and n can have 1 2 3 4 5 6 7 values. So I can say that my energy is quantized. Okay, as you can see that here my energy cannot have a value of 2h square over 8ma square. This energy cannot have a value of 2h square over 8ma square. Why the energy cannot have a 2h square over 8ma square? Because if I put 2 here, it becomes 4. Okay, and if I put 1 here, it becomes 1h square over 8ma square. So my particle cannot have energy 2 3. Okay, my particle cannot have energy between this and this value. Okay, similarly the next answer, if I put 3 here, the next answer comes out to be equal to E is equal to 3. 3 square becomes 9. The next answer is 9. Okay, so you can see that first answer is 1, the second answer is 4, the third answer is 9. The value cannot be in between 4 and 9. Okay, so this is the quantization of energy. So let's just derive the expression. For example, say we have a particle of mass m moving in a box. Okay, we have a particle of mass m moving in a one-dimensional box. Okay, so we have a particle of mass m moving in a one-dimensional box with that has a wave function. Okay, that has wave function equal to psi is equal to a sine n pi x over a. Okay, so for this particle we are going to derive the expression for energy. Okay, so first of all, as you can see here that my psi has a value of a sine n pi x over a. So next thing what I'm going to do is taking derivative on both sides. So if I take derivative of psi, it becomes curly psi over curly x. Okay, we have taken derivative with respect to x. Okay, so here I will also apply the derivative. So answer is, similarly here I have just applied the derivative. So on applying the derivative here, the answer that comes out to be is equal to, on applying the derivative, this a, since a is a constant, it will go out, a has come out. The next thing that I have is this n pi over a will be multiplied by this factor. Okay, this is the method of derivative, this is the process of derivation of these type of equation, that if I have curly over curly x into sine n pi x. Okay, if my derivative is being applied on such an equation, if my derivative is being applied on such an equation, then the answer comes out to be equal to this, the derivative, this n pi over a will come out, n pi over a will come out, and I have this sine, the derivative of sine is cos, it will become cos, and this n pi x over a will be written as it is. Okay, this is the method of taking derivative of sine n pi x over a. So I will apply this method here. So I have a constant that has come out, so I have derivative being applied on sine n pi x over a, derivative being applied on sine n pi x over a. My answer has comes out to be n pi over a cos n pi x over a, n pi x over a. Okay, so the next thing that I have is I am going to take the derivative again. So on taking on the derivative again, on differentiating again, this curly becomes curly square and this becomes curly x square. So now after taking the differentiative again, this a has remained here since it was a constant. On taking the derivative of this part, the derivative of cos comes out to be sine. First of all, I will write the derivative here, derivative of curly over curly x cos n pi x over a. So if I have a derivative of cos n pi x over a, the answer that comes out to be is, the derivative of cos is minus sine. Okay, first of all, this n pi over a will come out just like previous here. Okay, and the next thing, the cos is the derivative of sine minus sine, this minus will come out, and I have a sine here, and n pi x over a will remain here. So on substituting this value here, the answer is this n pi a over this n pi over a. I have this n pi over a. Okay, and the derivative of this part is this minus n pi over a sine n pi x over a. This minus will go out, minus a. This n pi over a will multiply with n pi over a, and the answer comes out to be n square pi square over a square. So I have sine n pi x over a. Okay, so this is the double derivative, this is the answer of the double derivative. So now as you know that we are talking about a particle in one dimensional box, you know that the equation, that the Schrodinger wave equation has the form h square h operator being applied on psi, so I will get an answer is equal to E psi. Okay, so now the next thing is, what I'm going to do is just to put in the values, to plug in the value of Hamiltonian operator. You know the value of Hamiltonian operator in case of one dimensional is, in case of particle in one dimensional box, we say that potential energy is equal to 0. We say that our potential energy is equal to 0 in case of particle in one dimensional box. Okay, the next thing is I'm going to put the value of Hamiltonian operator. The value of Hamiltonian operator is minus h cut square over 2m psi square curly x square, and that will come out to be equal to E psi. This part here is the Hamiltonian operator and this is the psi, and here E psi. Okay, I have taken potential energy to be equal to 0. As you know that during the calculation of the solution of particle in one-dimensional box, we take potential energy to be equal to 0. We assume the potential energy to be equal to 0. So we have assumed potential energy to be equal to 0. So we have a Hamiltonian operator of this form here, and this psi has just come from here. Okay, and this is the equal to and sign, and this is the energy value, and this is the psi again. So this is how I have put the value of Hamiltonian operator. So the next thing is, what I'm going to do is just to plug in the values. Okay, so I have a value of psi here, I have a value of psi here. Let's call it equation number 1, and I have the value of curly square psi. I have a value of curly square psi divided by curly x square here. Let's call it equation number 2. Okay, so I have equation number 1 and equation number 2. What I'm going to do is just to plug in the value of equation number 1 and equation number 2 in my equation number 3. So this is my equation number 3. So on putting the value, what answer comes out to be is, as you can see, that I have minus h cut square over 2m, h cut square over 2m. I have curly square psi over curly x square, that has a value of this. So minus a n square pi square over a square sine n pi x over a. So the next thing I have is equal to, in place of e, I'm just going to plug in the value of e, just plug in right e, and the next thing is I have to plug in the value of psi. The psi has a value to be equal to a sine n pi x over a, so I'm going to write this value here. I have the value equal to a sine n pi x over a. So the next thing that I'm going to do is cut this part from here, sine n pi x over a and sine n pi x over a, since both are the same. Okay, and this a is also present on both sides. This a will also cut down, and the next thing is this minus minus become positive. So what I'm left with is minus h cut square over 2m n square pi square over a square is equal to e. Okay, if I plug in the value of h cut square, h cut has a value of h over 2 pi. Okay, so if I have h cut square, then h cut square will have a value of h square over 4 pi square. So what I'm going to do is just to plug in the value of h cut square here. So when I plug in the value of h cut square here, the answer comes out to be equal to, and since this minus minus was consumed, so this become positive, so minus h cut square over 2m. So the next thing is, what I'm going to do is plugging the value. So plugging the value h square over 4 pi square into 2m n square pi square over a square is equal to e. This pi square will cut down with this, 4 to 8, 8 square, 4 to the 8 o. And here I have a square and here I have n square. Okay, so this is the value of e. E has a value, if I write it by, if I just rearrange it a little bit, I get a value of e to be equal to, e is equal to n square h square over 8m a square. So this is how we have derived the value of energy from Schrodinger wave equation for a particle in one-dimensional box. Okay, this was the energy is equal to n square h square over 8m a square. So this is what we have derived here. Okay, so our next conclusion is that when n is equal to 0, okay, so when n is equal to 0, the violation of Heisenberg uncertainty principle. We have a violation of Heisenberg uncertainty principle. What does it mean? Since, as you know, that energy has a formula n square h square over 8m square. If my n is 0, the value of energy comes out to be equal to 0. Similarly, if I have n equal to 0, then here this n will also become equal to 0 and my psi will also become equal to 0. So first of all, when my energy become equals to 0, it means that my particle does not have an energy. Okay, my particle has no energy, and no energy means that my particle is at rest. Okay, energy is equal to 0 means that my particle is at rest, and if my particle is at rest, then we can find the exact position and exact momentum simultaneously. Okay, if my particle is at rest, that means that if the energy is 0, then my particle is at rest, and when the particle is at rest, we can determine its position and the momentum, which is the violation of Heisenberg uncertainty principle, because Heisenberg uncertainty principle says that the position and momentum of a particle cannot be found simultaneously. But if my energy is 0, then the position and momentum can be found simultaneously. So energy cannot be equal to 0. because if the energy is 0, it will violate the Heisenberg uncertainty principle. In order to follow the Heisenberg uncertainty principle, the n cannot have a value of 0. So we can conclude that n cannot have a value of equal to 0. The other thing is that if my psi becomes equal to 0, then this will also be not true, because psi is the storehouse of the information. Okay, what is it? Psi is the storehouse of the information that cannot be equal to 0. Psi must have a value. Psi cannot be equal to 0. So when n is equal to 0, there is a violation of Heisenberg uncertainty principle, and secondly, we have psi become equal to 0, which is not true. So the third conclusion from the particle in a one-dimensional box is the existence of 0-point energy. Okay, we have a 0-point energy. The 0-point energy is at n is equal to 1. As we have told you earlier, that n is equal to 0 cannot be our 0-point energy, because at n is equal to 0 the particle becomes at rest, whereas at n is equal to 1 we have a value of energy to be equal to just like this. Okay, which shows that the particle is not at rest. It means that the particle has some energy, so the particle is not at rest even at 0 Kelvin. 0 Kelvin means absolute 0. Okay, if the particle is at absolute 0 Kelvin, then it will have an energy. Okay, whether or not the particle is at 0 Kelvin, it will still have an energy equal to h square over 8 ma square. Okay, this means that the particle will still be moving. Okay, if not at rest. Okay, if the particle is not at rest. Now what I'm saying is that I have n is equal to 1, so I have the energy. So if I have energy, so if my particle has energy, it means that my particle is moving. Okay, if my particle is moving, then the Heisenberg uncertainty principle is being followed. So we can say that for n is equal to 1, the Heisenberg uncertainty principle follows, whereas for n is equal to 0, our Heisenberg uncertainty principle is not followed. The fourth point is allowed energy levels. Okay, so let's just consider a box here. Okay, this is a box. Okay, so this is the length from 0 to a. Okay, this is the length from 0 to a, and this is equal, this n is equal to 1. This line represents n is equal to 1. This line represents n is equal to 2. This line represents n is equal to 3. This line represents n is equal to 4. As you can see that n is equal to 1 can have value of energy E1, that is equal to 8 square over 8 ma square. Okay, just plug in the value of 1 here. If I write the formula of energy, E is equal to n square h square over 8 ma square. If I plug in the value of n equal to 1, then I get an answer h over 8 ma square. If I plug in the value of n is equal to 2, then I get an answer 4h square over 8 ma square. Similarly, if I plug in the value of 3, then I get this answer. For 4, I get this answer. Okay, so as you can see that for a particular value of n, energy does not change. If I have value of n is equal to 1, throughout the length of the box, the energy remains the same. The horizontal line represents if I have a particle at this place, this place, this place, this, or wherever it is along this line, the energy is same. It means that my energy does not change along the length of the box for a particular value of n. As you can see that n is equal to 1 has a straight line, n is equal to still has a straight line. If a particle is present at this or this place, it will have the same energy for n is equal to 2. Okay, so this was the allowed energy level. So we have the energy levels of only n is equal to 1, 2, 3, 4 and so on. Okay, there is no energy level in between 1 and 2, 2 and 3, 3 or 4. There is no energy level in between. Okay, the energy level only allowed are n1, 2, 3, 4 and so on. The next thing is energy gap. So if I have delta E is equal to E final minus E initial, so if I take the n and I call it n plus 1, okay, I call the above energy level to be n plus 1, then you can see that my formula that comes out to be is delta E is equal to, in place of energy final, I have n plus 1 square h square over 8 ma square minus, in place of initial I have only n, this is the E1 and this is E initial and this is E final, so I have n square h square over 8 ma square. Okay, on taking the LCM I get 8 ma square, and the next thing is n plus 1 square h square minus n square h square. So what I'm going to do next is taking h square common. So taking h square common, I'm left with n plus 1 square minus n square. h square goes to the common and I have 8 ma square in the denominator. Now I will apply the formula of a plus b whole square on this part. So my answer that comes out to be is n square plus 1 plus 2n minus n square. Okay, so this is the formula, n plus n square plus 1 plus 2n, and this minus n square has come from here. Okay, and the next thing is h square in the common, and here it is at 8ma square. This n square will cut down with this, so I get an answer equal to 2n plus 1 h square over 8ma square. Okay, so whenever I am going to find the energy difference, I will have to use this formula. I can use this formula. Okay, I can use this formula to find the energy gap between any two energy levels. Okay, I can use this formula to find energy gap between any two energy levels. So here, as you can see that my energy level, the first gap between is 3h square. As you can see that my energy E1 has a value h square and E2 has a value 4h square. So if I want to find the difference, okay, so if I want to find the difference, then delta E is equal to 4h square over 8ma square minus 1h square divided by 8ma square, and after subtracting I get an answer 3h square over 8ma square. Okay, this is my energy difference. Next thing that I am going to tell you is that my energy is inversely proportional to the mass of the particle. What I am going to tell you is that my energy is inversely proportional to the mass of the particle, and the second thing is my energy is also inversely proportional to the distance. Here you can see that my energy is inversely proportional to the mass of the particle, and my energy is also inversely proportional to the length of the box. Okay, so it means that if I have a particle of larger mass, then the energy will be less. Similarly, if I have a box of greater length, okay, this box has a length equal to this, and if I have a box of length this, okay, if I have a box bigger box, okay, then it will have a larger length, and larger length means that lesser energy. Okay, so if I have a particle of larger mass and if I have a box of larger length, then my energy is reduced very much. Okay, if I combine this equation, then it becomes 1 over ma. Okay, as you can see here that if my mass is too much, means my mass is, the mass of the particle is very large, and the a here, the length of the box, is also very large. If both of these factors are very large, then the energy becomes very small. Okay, the energy becomes very small, and the smaller energy, what does it mean to have a smaller energy? The smaller energy means that I have this energy of smaller value, and if I have the energies of smaller value, then delta E will also decrease. Delta E will also decrease. Okay, so in the limit case, if I have a limit where a approaches to infinity, here if a approaches to infinity, I have a limit of a approaches to infinity, then the energy will become so low, then this energy difference will become so low that the quantization disappears. Okay, that at a is equal to, at a goes to infinity, my quantization disappears. So how does it disappear? As you can see here that my delta E, consider this equation, that my delta E is inversely proportional to the mass of the particle and the length of the box. Okay, so if I have a approaches to infinity, I have very large a, I have a very large box, then energy will become very low, because the denominator has increased, the answer will comes out to be very low. So I can say that if A is very large, then delta E comes out to be very low. If delta E, the energy difference between these lines become very low, then I can say that the quantization has been disappeared. The lines become closely spaced, so there will be no quantization. So that was the point number 5. So we have described 5 conclusions from particle in one-dimensional box. Okay, the first conclusion, what was the first conclusion? The first conclusion was the quantization of energy. The second conclusion was that when n is equal to 0, there is a violation of Heisenberg uncertainty principle. The third conclusion was existence of zero-point energy, and the fourth conclusion was the allowed energy levels, and the fifth conclusion was energy gap. And the further 6th, 7th, 8th, 9th and 10th conclusion will be described in our next videos. The link to the next video is given in the description. Okay, so see you in the next video.